Theorem 4.5 says that if a point A lies on the perpendicular bisector of a segment BC, so AX is perpendicular to BC and cuts it into two equal parts. If that's the case, then the point is equidistant from the endpoints of the segment. And what that means is that this distance and this distance is the same. Remember, that'd be a consequence of what we started with, because that's after the then. If a point is on the perpendicular bisector of a segment BC, then AB equals AC. And that's what we're going to try to prove. We've got to prove that given the if stuff, we can conclude the then stuff. So first of all, let's think about it. Remember, this is what we're trying to prove. We're not given that. We're given this is equal to this, and these two angles are right. And hey, bam, we know that this is equal to itself, because look, we got these two triangles. And by side, angle, side, going in order as we find them, side, angle, side, not angle, side, side, because that wouldn't be going in order. It's side, angle, side. By side, angle, side, we know the two triangles are congruent. So we're going to write that up in our proof. So 1. Of course, we put the given, so we know that AX is perpendicular bisector of BC, given. Okay, and as a result, we know that BX is congruent to BC. Definition, perpendicular bisector. I'll just abbreviate it like that or like that, whatever. Go this a little further apart from the BC. And we know, since AX is perpendicular to BC, we know angle 1 is congruent to angle 2. Remember, that's one of our theorems. A perpendicular makes two congruent adjacent angles. I don't remember which one that is in the book, so I'm just going to put perpendicular theorem, and you can look that up, see which one it is. And we know AX is congruent to itself. And that's identity. And therefore, as we talked about, by side, angle, side, side, angle, side, remember, side, angle, side, the two triangles are congruent. So triangle ABX is congruent to triangle ACX. Side angle side theorem. And then lastly, AB is congruent to AC. By our beloved CP-CTC. When triangles are congruent, the parts are congruent. Alright, that's theorem 4.5. Now let's try theorem 4.6. I'll do this one a little differently. I'll do this by contradiction. So, theorem 4.6 says, if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment. So we are given a point that is equidistant from the endpoints of a segment. Okay? That's all we started with. So we have a point in a segment, and this distance is the same as this, and I drew those distances in so we could visualize it. Now we want to see if A is on the perpendicular bisector of BC. Now we know that any point on the perpendicular bisector will be equidistant from the endpoints. So let's pretend this is equidistant from B and C, but it's not on the perpendicular bisector. Okay? So we're pretending it's not on the perpendicular bisector, it's somewhere else. Here's the perpendicular bisector, we'll pretend. That's just to visualize it, that's just for pretend. And we're going to see if we can still have this point. Now, between any 2 points there's a line. So what if, get that out of the way for now, what if I drew to the midpoint? Now, then we know that that is congruent to that. But this big triangle is isosceles. So this must be equal to this. But then by side angle side, these two triangles would be congruent. And that means that all the parts of the triangle are congruent. Remember CB, CTC? When triangles are congruent, corresponding parts are congruent. So since by SAS, we'd be able to show these triangles are congruent, and this angle must be equal to this one. Well, two equal angles along a straight line means they're each 90. So we have a contradiction. If we assume this point is not on the perpendicular bisector, then we conclude that this line is perpendicular, which is a contradiction to the fact that the point was not supposed to be on there. So it's impossible, in other words, for a point to be equidistant from the endpoints and then not be on the perpendicular bisector. So this is a good introduction to proof by contradiction. This comes up in philosophy, in physics, it can be important in law. In the history of physics, this is one thing that Galileo used to show that the old theory of motion was wrong. People thought that something would fall at a certain speed according to its weight. And maybe some people had thought about it before, I don't know, but so far as I know, Galileo at least made the most of pointing out that if this weighed 10 pounds, or let's say 50, and this weighed 10, then if they fall according to their speed, this weighs more, it should fall faster. But if you tied these together, then together they weigh 60, so this should fall faster than this one alone. But then how can that be possible? Because this one should want to fall at a certain speed and it should slow this one down. So we get this, all these like weird ideas, and we get a contradiction. Together they should fall faster, but this one should fall slower than the whole thing. And so shouldn't this one slow this one down, because this one wouldn't be able to get away from it? It'd be tied. And this one's falling slow and this one's held to it, so I can get away, but yet they're supposed to go faster alone. It's like, it doesn't make sense. I mean, it probably doesn't to you because that's a contradiction. Or what about if we put it like this? Then this one would be in the way, and how could this one go faster when this one's holding it up, even if they're not tied together? But then, considered as a whole, if it's 60 pounds, it should fall faster than just this one. It should fall 6 times faster than this one alone, but then this one's supposed to slow this one down. It's like, that theory doesn't even make sense. Which, it's probably not making sense to you, and that's good, because that's the whole point. The theory doesn't make sense. And that's just using proof by contradiction. So, we know that A must be on the perpendicular bisector, and let's go write that up. So, we started out with our given that AB is congruent to AC. Okay? We'll erase this so you kind of remember what was going on and what we did. Okay. So we drew those lines in there, but I'm not going to write that down. You know, between any 2 points there's a straight line, and that'd be postulates. If you want to put that in the proof, you can do that. AB is a segment, AC is a segment. One of our postulates. Okay. Now we know by one of our theorems already that angle B is congruent to angle C, and that's because, remember, when the sides of a triangle are congruent, the angles are congruent. It's like one of our isosceles triangle theorems. And then we're gonna, now we know A is on the perpendicular bisector or it is not. Okay? I'll kind of indent since I'm doing a contradiction. A on perp bisector or not. Okay, and that's just basic logic. We'll just call that we'll just kind of say for short now, like it is or it is not. You know, we can't say blue or yellow or red for a certain color because there's a lot of options, but you could say something's either on or off. You can say you're either dead or alive. You can say A is on the bisector or it's not. There's some situations where there are only two alternatives, so we can do something like this. Okay, now if A is not on it, we're going to pretend it's not. We draw the line segment that bisects BC. So we draw a segment that bisects BC because, you know, it's one of our postulates, 2 points determine the line. Okay, but since it bisects it, we know Bx and Xc are congruent. And that's the definition of a segment bisector. And then we know, as we said before, ABX is congruent to ACX by side angle side. I'm going to go ahead and erase this and start back up here. Make sure you can see it all. So we know we're on what, 6? So triangle ABX is congruent to triangle a CX side angle side, but then angle 1 congruent to angle 2 by CBCTC, but then they're both 90-degree angles. Let's see. I think there would be another theorem in the book that goes with this. I'm not going to look at it right now. I'll just put angle addition postulate, because this plus this equals 180, and you can divide by 2 and get 90. So it'd come from that pretty easily. And then AX perpendicular BC, definition perpendicular. But remember, that contradicts the assumption that AX is not perpendicular to BC. A is on perpendicular bisector of BC. I'll just call that is or is not again. And we'll have to like dig in some logic in class. But we assumed AX was not the perpendicular bisector, and that gave us a contradiction. So then we know, well then, A must be on the perpendicular bisector. And so then we proved it. Alright, so that might have been a little complicated, it's okay. You got introduced to a new type of proof, a new type of thinking, using contradiction to prove something. Like I said, that's important in history of physics, in philosophy and law, in reasoning in general. So it's really good to be familiar with it. And geometry is a good place to be introduced to it. Now let's look at theorems 4.7 and 4.8.